Okay, folks, welcome back. This is going to be the video part 3 of section 3.1, scatter plots and correlation. One thing I want to jump back to real quick is on the first page we did this example problem where there was times for track and field day at the in the AP statistics class. I hope you're getting in good shape and doing plenty of stretching and stuff, because we're going to do this one day. And I wanted to show you, I mentioned that we're not going to often do scatter plots by hand, even though we did in the notes this one time, and we will again here shortly. But I said most of the times we'll be doing scatter plots with technology. So I just want to show you how to create a scatter plot for this paired data, the sprint time and the long jump time. I want to show you how to do that on your TI Inspire. So you can see I already have entered the data here into a list and spreadsheet page. I'm going to add another page, data and statistics, and my horizontal axis, what is my explanatory variable here, was time. So I have the two variables to choose from. I'm going to select time, and now I simply go to add a variable on the vertical axis, and that's going to be length, for jump length. And you'll see that we have that same scatter plot that we created by hand, and now we have it nice and exact with technology. We're going to be doing a lot more with scatter plots in section 3.2, but I just wanted to make sure you had seen at least one time how to do that with your TI Inspire CAS calculator. Okay, so let's go ahead and get rid of that, and we're going to jump back into the notes page here now. Let's look at page 3. Example, salad at McDonald's. Well, we spent some time talking about beef at McDonald's in a previous lesson, so now we're trying to lighten things up a little bit here and go with the salad. So McDonald's restaurants offer a variety of salads. The table below lists 10 different salads along with the amount of sodium in milligrams and the amount of fat in grams based on their published nutritional information. The same data is also shown in a scatter plot. You can see the scatter plot right here. So we're asked to describe the relationship between sodium and fat in McDonald's salads. Discuss any additional observations you have about the data. Hint, look at the clusters. Look at the clusters. So let's take a quick look at the clusters of data here. We've got, and let's just go ahead and highlight them. I got a cluster of data right here. And let's take a look at, see if we can identify which points that which data points these are in our table. So we've got a value here of, well, looks like about, well, first of all, this one down in the corner here, that's got to be this side salad. All right, pretty low sodium, low fat. Then I'm looking for, let's just go backwards up this table. I'm looking for 180 milligrams of sodium and about 4 grams of fat. So that looks like it's going to be, that's also in this green cluster. Okay. In fact, I'm going to go ahead and color the other clusters so we can identify those as we go up the table. Okay, so the next one, we've got 740 milligrams of sodium and 18 grams of fat. So let's see, that's going to be 740, comma 18. Oh, that's way up here. That's definitely in the in that purple cluster. Caesar salad with grilled chicken, 580 milligrams of sodium and 5 grams of fat. That looks like it's this one in this lower left-hand grouping of the blue. And then we've got 300, well, bacon ranch salad without chicken. We got 300 milligrams of sodium and about 7 grams of fat, so that appears to be in our green cluster. Moving up the table here, we got a whopping 870 milligrams of sodium and 22 grams of fat. That's definitely up here in that purple cluster. And 700 milligrams of sodium and 9 grams of fat. That's going to be in this blue cluster. 150 milligrams of sodium, only 4.5 grams of fat. That's down in our green cluster. 820 milligrams of sodium and 21 grams of fat. That's, wow, that's way up here in the purple zone. And last but not least, 650 milligrams of sodium and 8 grams of fat. That's in the blue. So let's just double check. I should have 4 green dots. 1, 2, 3, 4. If you're colorblind, I apologize. I should have 3 blue dots. 1, 2, 3. And then 3 of those purple ones. 1, 2, 3. We're in good shape there. So I don't know. Do you notice anything? Let's take a look at the blues. Okay. We've got, one's got grilled chicken. This one's got grilled chicken. And this one's got grilled chicken. Okay, so that's something common about the three, that cluster of blue dots. Let's go ahead and look at the ones that are up here in this magenta area. Crispy, doesn't sound good. Well, this one's got crispy chicken too. And then last but not least, we got crispy here. So they must be doing something with the crispy chicken that jacks up the sodium and the fat. Maybe they start with salt and fat and then work backwards from there. I don't know. Then let's see the ones down in the green. Without chicken, without chicken, without chicken, side salad. Without chicken, I can assume. So definitely see a pattern there with respect to the type of chicken that it has, the type of chicken the salad has. Just in general, if you look at the pattern here, as the sodium salads with higher sodium content tend to have higher fat content. And let's go ahead and see what a good description would be for this. Definitely a positive association between sodium and fat content in McDonald's salads. Salads with higher sodium content also have higher fat content. I want to highlight a sentence here and talk about it real quick. Okay, the reason why I want to highlight that is because we talked about association in context with that sentence. If we just say there's a positive association between sodium and fat content, we're not going to get full credit. Okay, moving on. The relationship is fairly strong, but it is non-linear. Why did I make the conclusion that this is non-linear? Take a look at this overall pattern. Kind of starts low and then bends upwards. So that's why I made the decision to call that non-linear. And the scatter plot shows a curved pattern, and there are no apparent outliers from this pattern. Interestingly, there are 3 clusters of points: upper right, lower right, and lower left. These clusters correspond to salads with crispy chicken, grilled chicken, and no chicken at all. Even more interesting, within each cluster, there's a strong positive linear association. So if you look within each of these little clusters, there definitely appears to be a linear relationship. So that's a nice, thorough description of what I see in that scatter plot. Let's move on to this next section, which is called Correlation and Regression Applet Activity, and this is from your textbook TPS 5E. It's on page 152. You're going to need to look up this URL, and I know that's kind of tricky to type all of that into your web browser, so I would encourage you to not type it in, but go to Google Classroom, where I included a direct link to this applet. Okay, so I'm going to go ahead and jump off of the notes page now and take a look at the applet. Here it is. And let's go. The first thing says you're going to use the correlation and regression applet to make several scatter plots with 10 points that have a correlation close to 0.7. Start by putting 2 points on the graph. What's the value of the correlation and why does this make sense? So I'm going to go ahead and add points. Boom. Boom. We got 2 points on the graph, and all of a sudden it says my correlation is exactly 1. We're asked this question: why does this make sense? So remember what correlation does is it describes the direction and strength of a linear relationship. If I only have 2 points, well, there's exactly one line that goes through those points, and that would be perfectly linear. So the way that we're going to answer this question is as follows. The correlation is r equals 1 because 2 points determine exactly one line. Okay, let's go on to part B. And I want, again, I'm going through and showing you how to do this online. I want you to do it as well. I want you to try and pause the video and construct these scatter plots on your own to see if you can get the same result that I do. Okay, so jumping back over to the applet here. Make a lower left to upper right pattern of 10 points with a correlation of about r equals 0.7. Okay, so I got 2 points on here already. I'm going to go ahead and add several more. So I want to have 10 points total. Right now I have 7. So I got 9. There's my 10th point. Now I need to get a correlation of about 0.7. It says you can drag points up or down to adjust R after you have 10 points. So I'm going to take this one and kind of move it up this way. Drag this one down a little bit. So I'm trying to make the correlation worse, or make the linear relationship worse. I'm doing that by kind of putting more spread between these points. Oh, let's get rid of that one. All right, so I'm back to 10 points, and I'm going to continue to try and get some more spread between these points and get a correlation. Oh, there, I need to get rid of that guy. I'll get a correlation of about 0.7. That's about as close as I'm going to be able to get without sitting here for the next hour trying to get exactly 0.7. Okay, so there we go. We now know what a scatter plot looks like that has a correlation of about 0.7. And I could draw my own line of best fit through there. And then compare that to the actual line. So I'm not quite on, I'm off by a little bit. Okay, so let's go back and clear this scatter plot. It says part C, make another scatter plot. This one should have 9 points in a vertical stack at the left of the plot. So 9 points in a vertical stack. Points in a vertical stack. Add 1 point far to the right and move it until the correlation is close to 0.7. So I still have 10 points like I had before. I have this vertical stack on the left, and I'm going to take this guy and move it until I get a correlation of about 0.7, just like I had before, and that's about as close as I'm going to be able to get without sitting here for an hour trying to micro move that bad boy. Okay, so what's the whole point here? Well, I now have a scatter plot that looks a lot different than the previous one did. Previous one I had kind of clusters of points that had a general upward pattern. This one I've got this vertical cluster and then this guy over here that's way different than the pattern of the first 9 dots. But guess what? Correlation is still about 0.7. So let's see what we're asked to do in part D now. It says make a third scatter plot. Make this one with 10 points in a curved pattern that starts at the lower left, rises to the right, then falls again at the far right. Adjust the points up or down until you have a very smooth curve with a correlation close to 0.7. So let's clear that off. We're going to go ahead and do what they asked us to. We're going to add 10 points with a curved pattern. There's my 10 points. I've missed the goal of 0.7. I'm just going to kind of move some points around here and see if I can get to a correlation of about 0.7. It's a pretty tight curved pattern. And again, that's about as close as I can get to 0.7 without spending too much time screwing around with the applet. Okay, so now it's time to summarize. If you know that the correlation between two variables is r equals 0.7, what can you say about the form? What can you say about the form of the relationship? Well, remember, we've already looked at a couple different versions. We had a form that kind of went from lower left, upper right, was fairly linear but not strong. We had one with a stack of 9 points on the right, and then one off to the side that got us a correlation of about 0.7, and then this one we have clearly a curved pattern. So going back to answer this question, what can we say about the form of the relationship if we know the correlation is 0.7? And I hope this is pretty straightforward. We can say absolutely nothing about the form of the relationship. Okay, we need to see a graph of the data to determine form. And we just looked at 3 different examples where the correlation was about 0.7, but we had very different form in each of them. Okay, let's jump to the next page. In part 2, click on the scatter plot to create a group of 10 points in the lower left corner of the scatter plot with a strong straight linear pattern with a correlation of about 0.9. So let's go ahead and jump back to the applet, clear it off, and we're looking for 10 points down in the lower left corner with a correlation of about 0.9. Okay, so that's I got an extra point there. How did that happen? Okay, so let's go ahead and again try to get it as close as I can to 0.9. Okay, that's as close as I'm going to get. Now it says add 1 point at the upper right corner that is in line with the first 10. How does the correlation change? So I'm going to kind of look here and add a point, straight line up somewhere up here. It looks to be about in the same pattern. So let's see, how did the correlation change? Let me remove that point. How did I get 11 points, by the way? Okay, so that's a correlation, 10 points correlation close to 0.9. I'm going to add a point in the upper right hand corner that appears to be on the same linear path, and watch what happens to the correlation. Boom, it got a whole lot better. Okay, see that? Without the point, with the point. Okay, so again, by adding this point that's along the same general path of the original points, we definitely were able to get a correlation that was actually improved by quite a bit. So let's jump back and look at what this question asked us to do. How does the correlation change? Well, the correlation definitely, in this case, it improved. So adding a point that is different than the initial pattern can improve your correlation by quite a bit, and we'll talk about why that's not necessarily a good thing in a little bit. Okay, so let's jump back to this. It says drag the last point straight down. How small can you make the correlation? Can you make the correlation negative? Well, let's take a look here. I'm jumping back to the applet, and I'm going to grab this point and I'm going to just start dragging it down. Look what happens to the correlation. Okay, the correlation is getting worse, and in fact, yes, I can make it negative. Holy cow, so just that 1 point had a massive improvement when it was up here, and then just kind of destroyed our correlation when we went down this way. Okay, so let's jump back and kind of comment on that. Yes, we were able to get a negative correlation by pulling that point down. So, and again, let's think about what that does when we pull that point way down to the bottom here. Okay, what that does is it changes the overall linear direction. If you were to put a line of best fit through here, it's no longer got a positive slope, it now has a negative slope. And just that 1 point can change that line of best fit by that much. Okay, let's jump back to the question here. Let's summarize what you did, what you learned from step 2 about the effect of a single point on the correlation. So here's a good summary of what I think we should have taken away from this. An additional point that matches the overall pattern, even if it's far away from the majority of data points, does not have a large effect on correlation. In fact, it can have a large effect on correlation, but that large effect is kind of artificial. Okay, so that large effect can be kind of artificial. And then the second observation I have here is the additional point that does not match the overall pattern of data points can have a large effect on correlation as well. And again, we can see that. Artificially improving correlation and then kind of artificially decreasing it. All right, so that's in a nutshell what we want to learn about correlation from this lesson, section 3.1. We're going to continue to work with correlation in section 3.2, but I do want to stop right now and kind of finish this off with some comments about correlation. First of all, there's a formula for it, and I haven't showed it to you right now. I haven't showed it to you yet because it's frightening. I'm going to show it to you, but I'm going to first of all tell you that this is not a formula that you have to have memorized. It's one you'll never even use. I'm just showing it to you to illustrate that it is pretty complicated. And your calculator will provide correlation for you, and we'll see that once we get to section 3.2. But here it is. The correlation R is 1 over the quantity n minus 1 times the sum of x minus x bar divided by s sub x times y minus y bar divided by s sub y. So this is the sum of a product of two different quantities, and I hope these quantities look familiar to you. This one right here, well, that's the z-score for a specific point of x data. And this one right here, well, that's the z-score for a specific y value. Remember, we're talking about paired data here. And I want to jump back real quick to just look at some paired data. So what that z sub x means is we had sodium content here as our horizontal variable, so I could calculate the z-score for that 650. I would do 650 minus whatever the mean is of this entire set of data, and then divide by the standard deviation of that data. What about z sub y? Well, I could find the z-score for that 8 by calculating the mean of the entire list and doing 8 minus that mean, all divided by the standard deviation. That's what I mean by the z sub x and z sub y. So that's the first comment on correlation. The next comment on correlation, R makes no distinction between explanatory and response variables. It absolutely does not care if you switch the variables that you're calling explanatory and response in terms of horizontal and vertical. The correlation will still be the same. R is not affected by data transformation, so we were looking at that example of milligrams of sodium and fat grams. If we change those to a different dimension, so if we measured sodium in, I don't know, ounces, and then we measured fat in pounds, if we did that transformation of the data, correlation between the two variables would still be the same. R is just a number. It has no units. So if somebody says, oh, the correlation between those two variables is 0.9 meters per second, you'd be like, oh, that's false because R has no units. Both variables must be quantitative, and that's another thing that could come back to bite you as a student. If you're asked, hey, what's the correlation between height and eye color? Oh, well, that's absurd because eye color is not a quantitative variable, it's categorical. R only measures the strength of linear relationships. So if you see a curved pattern in your scatter plot, it doesn't make sense to use R as a descriptor for that data set because it only measures the strength of linear relationships. R is not resistant to certain types of outliers, and we kind of saw that with this regression applet. Okay, so it doesn't resist the pull of this outlier way out here, and we'll talk more about outliers in the horizontal direction and the vertical direction as we get into section 3.2. R is not a complete summary of data. You still have to graph your data. I want to show you a quick example now of what I mean by you still have to graph your data. I'm going to show you a graph where the correlation, the graph is going to change, but the correlation will always stay about the same. Let's take a look. So you'll notice here that the correlation is always about negative 0.06, regardless of the pattern of the data. In fact, we can even go to our friend the T-Rex and notice that this correlation is not changing, and that's because the correlation measures the direction and strength of a linear relationship. If the relationship's not linear, it doesn't make sense to use that correlation. So the message here is to make sure you always have a picture of your data. You have to graph your data to make sure you're using correlation in the correct context. The last thing I want to share here, and this is a big one, folks. This is maybe the one big takeaway you have from AP statistics. 20 years from now, you'll be like, I remember that one thing that we talked about a lot, and that's correlation does not imply causation. Just because there's a correlation between two variables, like, for example, sodium and fat content in a sandwich, doesn't mean that one causes the other. And we're going to spend a lot of time talking about that as we get into our chapter on creating experiments and designing samples. We'll talk about correlation, and it does not imply causation a lot in that chapter. Okay, folks, that's it for section 3.1. Please, if you have any questions, make sure you don't hesitate to ask.